Yeah, thank you very much and for the nice introduction and for the invitation. So maybe let's start with the following. So we have sigma. Let's assume a closed manifold and X vector field. And then we have the flow of X. So this is phi tx from sigma to sigma, t in R, and this is defined by phi 0 of x is the identity of sigma, and d of dt, phi tx little x, this is vector field at position phi tx of x. So we have here is our sigma, and we have these are just the integral curves, so we always have a vector field x of x, and we follow this vector field. And the dream of every people working in dynamics is understand this flow. If one understands this flow, you can predict everything. Future and past. You can go to negative times, to the past, and you can go to the future, to positive times. So that's the somehow the dream. Understand this flow. And now global surface of section is kind of a tool to come a bit closer to this dream. So what is a global, maybe a disk-like global surface of section? So this notion goes back to Poincaré and Birkhoff. Also Poincaré didn't really consider disk-like, more annulus-like, but so Poincaré, Birkhoff. So let us assume that our so sigma is just S3 and X is nowhere vanishing. So we have no fixed points of this flow. And then what is a global surface of section? So E in S3, this is two-dimensional. This is an embedded two-dimensional disk. So you can imagine we have here our room is S3 and we have here is our disk, and this should have the following properties. So first, at the boundary the vector field is tangent, so that means that the boundary is actually a periodic orbit. So we have the vector field here at the boundary is like this. So X is tangent to the boundary of D. That means dd is a periodic orbit of X. And second condition is in the interior, it's the opposite. The vector field is transverse to D. So it's never tangent. Either it always points this direction or always into the blackboard. So X is transverse to, so I make here this circle, so that's the interior of D. So X is transverse to. So these are kind of local conditions at at this disk, but then there is a third condition, the global condition, and the third condition is that if x is any point on sigma, on this any initial condition, so x is any point in this case just S3, then there exists a positive and a negative time so that the flow will hit this disk. So there exists t plus, actually depending on x, bigger 0, and t minus, depending on x, less than 0, such that phi t plus x of x in d and phi t minus little x is also in d, i.e. The flow through x hits d in forward time in the future and past. And then you can iterate, so you can apply this again, so we will actually hit this disk-like global surface of section infinitely often in the future and infinitely many often in the past. Yeah. That's this notion of disk-like global surface of section. Is clear? Other questions? So suppose we have such a global surface of section. So what can we do with this? So then, as I suppose D3 is global surface of section. So then we can define the Poincare return map. So let's say this is from the interior of D to itself, and it's the following. So if you have point x in the interior of D, then we have tau x. This is the first first time where you come back to the interior of D in the future. So that's the minimum of all t bigger 0, such that the flow of x is again in D. So the first return time in the future. And then psi of x, that's just phi tau x of x. So if you have, here's our disk. So we have some point x here, and then we go out, interior, the vector field is transverse, so we go out, and then once we come back. And so this is psi of x. So, and the information about the dynamics on this, for this continuous flow, or the smooth flow on S3, is basically preserved now on this disk, on this of this disk map. So, for example, if you're interested in finding periodic orbits different from the boundary of D, then this just corresponds to the periodic points of psi. So somehow you discretize your problem and you reduce the complexity of the problem by 1 dimension. Yeah.
So in your dynamics on S3, then you assume that the minimal period of this vector field is positive and
Not all orbits are periodic. Yeah, but there is not all are periodic. But of course there is a minimal period. Yeah, it is positive minimal period. Because you have you cannot come in arbitrary small time back to the disk. So no. Periodic orbits of X on S3 different from the binding orbit, from the boundary of the disk, they correspond to a periodic points of psi. So it's useful gadget, but now the question is, does it exist? So question, does a global surface of section exist? And in general, no. There are obvious obstructions what you have, namely what you first need to have is you need to have a periodic orbit. Otherwise you don't have a boundary. So obvious obstructions so we need to have a periodic orbit. Need periodic orbit, namely the binding orbit, the boundary of D. But then this orbit also has to have some special properties. So this is a periodic orbit in S3. So you can think of it as a knot. But because we have here embedded disk, this means genus is 0, so it has to be an unknot. So this is actually an unknot because it bounds embedded disk. And an additional obstruction, an obvious obstruction, is if this binding orbit is also linked to all other periodic orbits. That's because the vector field is transverse in the interior. So if you have another periodic orbit, so it go several times around, but then the linking number you can just count how many times you intersect, and then it's plus minus this number, but it's always in the same direction, so there is no cancellation. So we have the additional ED is linked to every other periodic orbit. Make the picture. So here we have the DD. And if you have another periodic orbit, this is a periodic point of this Poincare term map. So you have this. Then you go But then you always, because you always transverse, you just count how many times you hit this global surface of section. So there are obvious obstructions. And now what are holomorphic curves good for? So holomorphic curves, they reduce. So the question about existence of this disk-like global surface of section, this is a question about for all orbits, because of this global condition. So also the non-periodic ones, they have to come back to this disk-like global surface of section. But holomorphic curves, what they can do, they reduce for reflows the question about disk-like global surface of section just to a question about periodic orbits. So so holomorphic curves reduce a question about existence of global surface of section the question about periodic orbits for reflows. So your flow has to have some special feature, otherwise we cannot really use this global surface of section, these holomorphic curves. Now, let me remind you what is a reflow. So reflows. So first, for reflows, first we just need that sigma is odd dimensional. So we have sigma and S1. This is odd dimensional. Maybe let's assume it's closed. Closed manifold. And then a contact form, on sigma, that's lambda, that's one form on sigma, such that lambda wedge d lambda to the n this is a volume form on sigma. And then if we have such a contact form gives us dynamics. Namely, we can define a vector field. So then we can define the Reed vector field. And this is defined by the condition. So if you plug in lambda to the one form, this is 1. And if you plug it into d lambda, then this is 0. Because of this non-degeneracy, so this is uniquely defined by this condition. And then let me also mention the contact form also gives us a contact structure. Contact structure. So that's psi. This is the kernel of lambda. So this is a hyperplane distribution. And so we have, if this is sigma, they look odd dimensional, but you should imagine some more dimension. So at each point we have a real vector field x, and then so the real vector field is not in the hyperplane distribution. So we have here 1 is not in the kernel. So we have here psi of x. So we have a splitting tx of sigma. This is this vector space, this of the hyperplane distribution plus the span of the real vector field. So this is span. And this hyperplane, this psi is actually a symplectic vector bundle. So so we have so psi over sigma. This is tangent bundle, and so this is a rank. If the whole thing is 2n plus 1, this is a rank 2n symplectic vector bundle. And why it's symplectic, I can just restrict d lambda to psi. Namely, if I can look at d lambda, restrict it to psi. Then I have symplectic vector bundle. Okay, so then, and now I have dynamics due to this real vector field. So suppose we have such a contact manifold, so sigma together with a contact structure, then we can associate to this the symplectization. So the symplectization this is just sigma times r, but sigma times r, this now is an exact symplectic manifold. Namely, if I have here I have x here and r real number, then I have er lambda. So this is just er batch lambda plus er d lambda. This is a symplectic form on sigma times r. And so psi and real vector field I just extend trivially to extend psi and r trivially to sigma times r. And now this here I have another obvious vector field. I have also the dr. Then if I have here a point xr in sigma times r, then the tangent space txr sigma times r, this now we have the psi x plus, and then we have the span of the real vector field and dr. And this is actually a symplectic splitting. So I have here a symplectic subbundle, and here I have a symplectic subbundle. So I have some symplectic splitting. And now on the symplectization, I look can look for special kinds of almost complex structures. These are so-called SFT-like almost complex structure. SFT-like almost complex structure. On the symplectization sigma times r. So what I choose for this SFT-like almost complex structure. This is determined. I have to choose one almost complex structure on this Xi, on the symplectic vector bundle. So I choose omega compatible. So this is omega. Almost complex structure. On Xi, let's call it J on Xi. That means that if I plug J into omega, I have a Riemannian metric on Xi, and this is almost complex structure, so J square equals minus identity. And then I extend it in such a way that it's R invariant, and so then I have it here, and then I require that I map the Re-vector field to minus dr and er to the Re-vector field. So then extend J R invariant to omega compatible almost complex structure on sigma times R, such that J of dr is minus R and J of R is R. So I have both of these symplectic subspaces. They are invariant under J. I have Tx R sigma times R. This is psi x plus x R, and then so J, oops, psi is invariant under J, and this is also invariant under J. So this, and it's the whole thing is R invariant. This is SFT-like almost complex structure. And okay, and then I can study holomorphic planes. So holomorphic plane so I choose so J SFT-like almost complex structure on sigma times r, and then I look at, let's go at u tilde from C to sigma times r, so maps from the complex planes to sigma times r, solution of the following nonlinear Cauchy-Riemann type equation. Solution of dx u tilde plus j at u tilde dy u tilde 0 if I write z equals x y c. So this is our nonlinear Cauchy-Riemann. And actually I have on these solutions, I have an R action on these solutions. This is because I have chosen this J R invariant. So if I write, u tilde equals u a, where u is mapped from C to sigma and a is mapped from R, from C to R, then and so suppose u tilde equals ua is a solution of star and R is a real number, then I define R star of u tilde. This is just u a plus r, and then r star u tilde is also a solution of this equation because J was R invariant. And it follows J R invariant implies that R star u tilde is also a solution of this nonlinear Cauchy-Riemann equation. Then so we also have a notion of energy for this holomorphic. First it's just holomorphic plane, but now what is the energy? So we look at the space gamma, phi, smooth maps from R01, phi prime bigger or equal 0, maps like that. Monotone. And if phi is in gamma, then let's abbreviate lambda phi. This is one form on sigma times r, and it's defined as lambda phi at the point xr. This is phi r of lambda x. In sigma times r, and then if u tilde from C to sigma times r is a solution holomorphic plane. So solution of star define E U tilde. This is the supremum over all phi in gamma. So they take the integral U tilde star E lambda phi. So this it could be infinite, but what you can check is because J is because it satisfies this holomorphic curve equation, it's never negative, and it's 0 if and only if U tilde is constant. So some fact or some exercise or exercise. So use star to show E U tilde is actually is never negative. So it's non-negative. And it's 0 if and only if U tilde is constant. And then now define finite energy plane, one where EU tilde is not 0 and not infinite. So not a constant one, but also not infinite. So definition, U tilde solution of star is called finite energy plane if the energy is finite and non-zero. So this notion, this was of finite energy plane. This was also introduced by Hofer, also introduced by Hofer, and he had some special reason to introduce it. Namely, if you have finite energy plane, then you also get periodic Reeb orbits, also connection with periodic Reeb orbits. So what is a so gamma? Let's call it a smooth map from S1 to sigma. It's called periodic Reeb orbit. If there exists tau bigger 0 such that gamma solves, so gamma dot of t equals tau r gamma t in S1. So I identify S1 with r mod z, and then this tau, this is kind of the velocity, or you can think of it as the period, because I make my period always 1, but I change my speed. And after, if you reparameterize, you can also think you keep the speed. You have the speed of the Lie vector field, but then the period is tau. So I will refer as tau to the period. So tau is the period of gamma. And then, so suppose we have some finite energy plane, then there exists a Reeb orbit So the theorem of Hofer was that if U tilde equals UA is a finite energy plane, and then there exists gamma, periodic Reeb orbit, and a sequence Sk going to infinity such that if you look at so the maps U so you can look at the maps T goes to U e to the I S k plus 2 pi t. So this is a sequence of maps from the circle to sigma. So this is, maybe let's call this so UK. This is bound to sigma, defined by convert, satisfy UK as k goes to infinity, they converge to gamma. Sorry. This I is wrong. That's sorry. Sk plus 2 pi I t. Yeah, sorry. So I'm on my complex plane. So I look here at bigger and bigger circles. Here is e to the sk plus 2 pi I t. I restrict my map here, and then if sk goes to infinity, I converge to gamma. So that means, so as soon as I have a finite energy plane, I also have a periodic Reeb orbit. And this was used by, so maybe you've heard of the Weinstein conjecture. So the Weinstein conjecture is a question: does on every contact manifold exist periodic Reeb orbit? And this is now known in dimension 3. In high dimension is still open, but this theorem of Hofer, this was some important ingredient to prove it for many three-dimensional manifolds, because as soon as you have this finite energy plane, you also get periodic Reeb orbit. So this was used to prove some version, some special case of the Weinstein conjecture.
Topology you use?
So C infinity topology. So you can even make the statement a bit stronger. So then you can say for any sequence going to infinity, you can find a subsequence that you have this. So we have, so if you have these finite energy planes, they come with some obvious symmetries. So we have kind of gauge action on finite energy planes. So note that this energy is actually invariant under the R action. So note we have the energy of R star U tilde is E U tilde. So energy invariant under R action. So that means if you have a finite energy plane, all its R translates are also finite energy plane. So if U tilde, U tilde is finite energy plane, then R star U tilde is finite energy plane. So this R action, this is actually action on the target. So you have U tilde from C to sigma times R, and then here on the target we have this R action, but we also have action on the domain by reparametrization. Then we have also reparametrization of domain, and these are the direct similitudes, the biholomorphic maps from C to C. So we have here an action of C star C, the direct similitudes. So this, if we have let's call W in C. C star is, with C star I mean C without 0, and V in C, then I have the action of WV star. And also Z in C, Z, this is V Z plus V. So this is, geometrically, this is a dilation and rotation and translation. So these are the biholomorphic maps of C to C. Biholomorphic maps. From C to C. And then, so they act on these finite energy planes by reparametrization. So we have, so then we have, if V star U tilde, so we define this just as U tilde of Vz plus V Z in C. So this is just reparametrization. And because this is holomorphic, then after this reparametrization, U tilde still satisfies the holomorphic equation. And these two actions commute, or they don't see each other. So actually we have an action of C star unfortunately semi-direct because they don't really commute. So the semi-direct product of C star and C and R on this finite energy plane. So both actions commute. So we have an action of C star C times R on finite energy planes. So let me make an example where you can actually see this line. So this is a bit unfortunate. Usually we can write down the equation, but usually it's very hard to see it because this J, they always exist, this SFT-like J's, but it's hard to write it down usually explicitly. So it's rare that you see an explicit finite energy plane, but so there is an example where you can see it explicitly. So example. So the example is we take so our contact manifold is S3 in C2. So we think of S3 as the Z equals Z1, Z2 in C2 such that Z1 square plus Z2 square equals 1. And then we have here we have the contact form. So we have the lambda equals x1 d1 1/2 minus y1 x1 plus 1/2 d x2 wedge d y2 minus y2 x2. This is a one form on C2, and if you restrict lambda to S3, then we have a contact form. And the reap flow is in this case just a Hopf flow. So the reap flow, this corresponds to the Hopf flow. So if we have Z equals Z1, Z2 in S3, and then we have phi RT of Z1, Z2. This is just e to the 2 pi I t Z1 e to the 2 pi I t Z2. So this is a bit rather special flow. So for this flow, all orbits are periodic orbits. So this is, of course, in general not true. The dynamics is here not so exact as well, not very complicated. And what is the symplectization of this S3? So this you can just think of C2 minus the origin. So the symplectization symplectization S3 times R, you can think of this as C2, the origin. So if you have Z and R, you just map it to the e to the R Z. So it's so this is 3, and then so we take out the origin, and then we have here this R action. And in this example, actually I, so multiplication by I, this is SFT-like almost complex structure. Then, so I, as a multiplication by I, this is SFT-like almost complex structure. And then, if A is, I mean, or maybe I use already A for, so let's call it maybe W. If W is in C star, also in C0, then the map Z goes to ZW. This is a finite energy plane. Holomorphic for I. And so what is the asymptotic orbit? So the asymptotic orbit is just if you go to infinity, then you can ignore this. So you will see the circle here. So the asymptotic Reeb orbit. This is in this case t goes to e to the 2 pi I t 0. So these all of these finite energy planes, they are have the same asymptotic Reeb orbit. This here. And then you also know, because of this this action, so we can actually, some of them are equivalent. So note, so this one, ZW, this is equivalent if you use the R action, so use the R action to the one where we just map 1 over W Z W by W, and then we can reparameterize again. So this is just the dilation. So we dilate again. So we use the reparameterization. So this is equivalent to the Z goes to ZW divided by W, absolute value. So now this parameter W, if you just divide by its norm, then we have a circle. So we have actually so up to equivalence, this is a circle family of finite energy planes. So we have yeah, yeah, not too hard, but maybe let's exercise. So yeah, so it's it's not completely obvious, but it's also not too hard. So yeah, maybe exercise show that this energy is actually finite. But actually, because it converges, as soon as it converges, energy will automatically be very finite by Stokes. So you can estimate with the period of the asymptotic orbit.
By the way, so this J, in this case, J sends dr to R.
Yes.
You wrote before J sends R go to dr, and J of dr goes to minus R, right?
Okay. Maybe so you can switch this. Yeah. Okay. Maybe you should switch the sign. Yeah.
So radial one is going
The radial one goes to. All right. Here it goes. The radial one goes to R. Yeah. It's opposite. Yeah. Yeah. Right. Good. So we have a S1 family of finite energy planes. So if you have EI theta in S1, unit circle C, Z goes to Z to the I theta. And now, so as I said at the beginning, so our interest is find global surface of section, and so global surface of section, this should be disk, or the C is diffeomorphic to open disk, which have these properties. And now if we have finite energy plane, so our candidate for global surface of section is the U. Or the A we actually don't need. This is just this R action. But the U, this is a map from C, open disk, to sigma. And so if we look just at the U, not the U tilde, so we just divide by the length. So we have the. So this is kind of let's call this U tilde. Let's call it maybe U tilde theta of Z. This is this, and then the U theta of Z. This is then 1 over Z squared plus 1. E to the I theta. So this is so U theta. This is a map from C to S3. And so we have this S1 family of maps, and what they do is they give us an open book decomposition of this S3. So this gives open book decomposition of S3. And how does this look like? So it's a bit difficult to draw because the blackboard is just 2-dimensional and we have here 3-dimensional. So I cheat by 1 dimension. So So I cheat by 1 dimension. So so this asymptotic orbit, rib orbit, I draw like a point. And then the planes I draw one-dimensional, also they are actually two-dimensional. So this point, which is actually a circle, you can think of the binding of the book. And then this circle family, these are the pages. So this looks like this. So we have So these are the images of this U theta. So we have this S1 family, and all of them asymptotic to this rib orbit. And if you look at the flow here is not too exciting because it's just periodic. But what is the flow? The flow is, this is here, so it transverse, and it goes just around like this. So if you look at the flow, then so you can start here, and then you just because it's periodic. So because it's periodic, the Poincare return map is actually the identity. So this is here in this case is periodic. But what is interesting to note, and so all of the members of these S1 families, all the pages, they are actually global surface of sections. So we have a whole S1 family of global surface of section. So we have so all pages are global surface of sections. So the flow here, the flow is a bit very easy. So this picture, this is quite a general picture. So this picture one tries to get in many different cases. In the more complicated cases, we can write down the things like here, but that we get such an S1 family of finite energy planes, such that which give an open book decomposition, so that all pages are global surface of section. This will be a general theme. We will see in much more cases. The flow here is very special. So here the flow, this is just periodic, and the Poincare return map is just this is just identity. But what we try to use is finite energy planes to get these pictures, but with a more interesting flow. So with holomorphic curves, so of course I had to explain, it's not always this case, but so that's in good cases, one gets in good cases the following picture. So the first picture is the same, so we have, again, S1 family. So we have S1 family of global surface of section, and this is just, we have S1 family of finite energy planes, and we project to the first coordinate, the first to U. So we have a S1 family of global surface of section. But then the flow will be in general much more complicated. So it starts here, but then it comes back somewhere else, like this. So. Okay. Is this general picture clear? So let me make some remarks about the asymptotic Reeb orbit. So in general, it doesn't need to be unique. And there are actually examples, recent examples by Siefring, where you can see that a finite energy plane can have different asymptotic Reeb orbits. So remark, in general, asymptotic Reeb orbit not uniquely determined by a finite energy plane. And these are also example. But it will be unique if it's non-degenerate. If non-degenerate, then uniqueness follows. And so what does it mean non-degenerate? So what is a non-degenerate periodic Reeb orbit? So recall, we have as a periodic Reeb orbit this solution as a gamma t. This is just dot is just tau r gamma t, or we can say gamma time t is the Reeb flow time tau t applied to gamma 0. And so note that the Reeb flow preserves lambda. So note phi t r star lambda is lambda. So where is this? This is just the easy exercise with Cartan. Also Cartan formula. If we look at the Lie derivative, of lambda, this is I r d lambda plus d I r lambda, where IR is just the map you obtain by plugging in R into d lambda. But this here is 0 by the first property of the Reap flow, and this here is constant 1, so d of it is also 0. So this is 0, and therefore it preserves lambda. So that means we can, if we restrict the flow to psi, the differential of the flow to the hyperplane distribution, this remains invariant, and we have a family of symplectic maps. So the consequence is that the differential of TR at x, this maps psi x to psi phi TR of x. So here we have x, and then we have psi of x, and so we map, here we have phi tr of x, the corresponding psi phi tr of x. And this is symplectic. This is symplectic. Symplectic linear map. And in particular, because it's periodic, so if you have a periodic Reap orbit, the differential maps the tangent space to itself. So we get d phi tau r of gamma 0. This is from if we restrict it to psi gamma 0. This is a map to itself, a symplectic map. And we say it's non-degenerate if there is no eigenvalue to 1. So gamma is non-degenerate only if d phi tau r gamma 0 restricted to this psi gamma 0 minus identity of psi gamma 0 determined. Then if it's non-degenerate, then we have a unique asymptotic Reap orbit, because this then also guarantees that the periodic Reap orbit is isolated. So unfortunately, the example we had is that it's degenerate because there everything is periodic. So this is kind of a more spot. This is kind of more situation, and the example is kind of more spot situation, but. This is quite unusual that it's not unique. So even more general case, when it's more spot, it's still okay. And so as you see in the example, you can still have still uniqueness there of the asymptotic Reap orbit. But there might be very strange examples. And so in the following, we will assume that it's non-degenerate. Yeah.
In simplest example, The Birkhoff construct in S3 or
I think it's, you can.
S3?
Maybe it was not in S, but I think you can also make in S3 examples. You start spiraling around. You have an S1 family of periodic orbits, all degenerate, and then you spiral around, and then all of them are in the limit set. Yeah. You have to really work hard to find examples. So it's not. This is not the usual case, but in following we will just assume that we have non-degenerate ring orbit. Good. Okay. So now to get more information on this finite energy plane, we also need the Conley-Sender index of this periodic Reeb orbit, but I will give a probably not standard definition of Conley-Sender index, and the definition I give you only works in dimension 2. So I give you some kind of binding number definition of the Conley-Sender index, and this does not work in higher dimensions. So up to now everything works in all dimensions. You can look for these finite energy planes in every dimension, but in the following we will restrict to dimension 3, and this has also, you can understand the geometric reason for that, because if you are in dimension 3, the symplectic ization is 4-dimensional. So we have 2-dimensional things in 4-dimensional space, and they have very interesting intersection properties. So this is like lines in dimension 2. So you have isolated intersection, but they are rigid, so you cannot get rid easily of them. So that's why we have this theory is very special in dimension 4. In higher dimensions, this is kind of SFT. This is extremely hard. So Suguru is not here, but you can ask Suguru. You can ask Suguru about SFT in general. But what we need for this lecture is just in dimension 4, and there we have more structure. We have this intersection properties, and that's also why we have a very special Conley-Sender index. So yeah, that's the next. So Conley-Sender index. In dimension 2. So it's dimension 2 because the dimension which counts is the hyperplane distribution psi. So the contact manifold will be 3-dimensional, but the hyperplane distribution 2-dimensional. So we have psi from 0, 1 to in this case it's just SL2R. It's a symplectic maps in 2 dimension. In 2 dimension, the only thing which is symplectic is you preserve the volume. So they have to have determinant 1. So this is the linear symplectic group in dimension 1. This is some continuous path, and we start psi of 0 is identity. And we can also write dt psi. Maybe let's assume it's smooth. So we write dt psi. This equals j s psi, where j is R2. So this is the multiplication by I in R2, which R2 we identify with C. As matrix J is just 0, -1, 1, 0, and S. So S is some t-dependent symmetric matrix. ST is symmetric matrix. ST is ST. This is a symmetric 2 times 2 matrix. And yeah, instead of studying psi, we can also start S. So they uniquely determine each other. And so the Koenig-Sandler index we actually associate to such a path of symplectic matrices. And now, to study this path, one can study S, and instead of studying S, we can study the following operator. We look at the following operator. Consider AS. This is to C to L2 of S1 C. The C is always, I think of C as R2. And this maps V to minus J dtV minus STV. So this is Sobolev space. We have one quadratic integrable derivative. So we can take here derivative, and then we get, this is a Fredholm operator from this Hilbert space to this Hilbert space. And now we study eigenvectors, the eigenvalues of this Fredholm operator. So suppose eta is an eigenvalue of AS. And then so then we have a V an eigenvector to eigenvalue E to eigenvalue so that means ASV equals eta V. But we can, because of the special form of this operator, we can, this V actually is a solution of the following ODE. So it means that V is a solution of the ODE minus J ETV equals S plus eta V. Let's call this star. And V is an eigenvector, so it should not be identically 0. But if it's not identically 0 and it satisfies its first order ODE, it has to be non-zero at each point. Otherwise, if it would be 0 at one point, because the solution of this ODE, it would be identically 0. But since V is not identically to 0, also not 0 at every point, this equation, this ODE implies that Vt is different from 0 for all t in S1. And this is just, this is just a complex number. Now we can look at the following. We get the map from S1 to S1, namely t goes to Vt, and then we normalize. And this map has a degree. So we define W of V. This is the degree of the map T goes to Vt. So that's set. So you look how many times you wind around S1. And now there is a lemma which was observed by Wysotsky and Sender. So you can think of this as binding number of this eigenvector. But now the lemma is that this actually only depends on the eigenvalue and not on the eigenvector. So that has this a bit strange consequence that we can talk about binding number of an eigenvalue. This sounds strange because we have just a real number. What should be the binding number of a real number? But because we can associate the eigenvector, and it's independent of the choice of the eigenvector. The lemma over Wysotsky and Sender if V1, V2 are eigenvalues to the same eigenvectors to same eigenvalue, then it follows that they have the same binding number. So let's prove this lemma. So if V2 is just a scalar multiple of V1, then it's obvious. So V2 scalar multiple of V1, then follows lemma is obvious. So therefore we can assume without loss of generality that these two eigenvectors are linearly independent. So therefore without loss of generality, V1, V2 are linearly dependent. Now define V from S1 to C by T goes to V1 of T, V2 T bar. Here my complex conjugation. Complex conjugation. And then I have the degree of the map T goes to Vt, Vt. So because this is, this is additive under multiplication, but here we also reverse we go backwards, so we get the minus. So this is the degree of the map T goes V1 T absolute value minus the degree of the map T goes to V2 T V2 T. And I want to show that this here is that this degree is independent. So these two should be the same. So I should show that this here is 0. So to show the degree of T goes to Vt T value, this is 0. And to show this, also I claim that Vt is not in R for all T in S1. That's a proof of claim. So by contradiction, so as soon as I have, as this claim is true, I know this, because if I never in R, then my map does something like this, but I not like this, just here. Also not like this, just like this. So I, and then I can. No, so as I'm on the unit circle, so I go like this, then I can homotop to 0. So as soon as we have the claim, we have this. So let's prove the claim by contradiction. And so assume there exists T0 in S1 such that V of T0 is in R. But that means that there exists tau in R. So if you remember the definition of V, this is just V1T, V2T bar. So that means at this time, the two V1 and V2T at T0, they are linearly dependent. so there exists t in R without 0 such that v1 t0 equals tau v2 t0. So they're linearly dependent at one point. But because of this ODE, if they're linearly dependent at one point, they're always linearly dependent. So define V3 from S1 to C as this is V1 minus tau V2. And so we have V1 and V2 are eigen vectors to the same eigenvalue. So we have A V1 equals A eta V1. A V2 equals eta V2, so it follows that A V3 equals eta V3. It's also, also V3 is also an it's either 0 or an eigenvector. So let's just call this maybe star star. And V3 of T0, this is V1 of T0 minus tau V2 of T0. So at T0 it's 0. But star star means this V3 is also solution of ODE. And so if it's 0 at one point, it's 0 everywhere. So then it follows with star star V3 of T is 0 for all T in S1. And that means that V1 and V2 are linearly dependent, which we just assumed they are not. So it follows V1, 2 are linearly dependent. That's contradiction. And now we prove the claim. And this proves the lemma. Okay. So now this lemma has some funny consequences. So first we can now define the winding number of an eigenvalue. So consequence of lemma suppose eta is right. So it's in the spectrum of AS, meaning that it's an eigen value. There's a spectrum, i.e. eta is an eigenvalue. Yes. Yeah. So as a matter of fact, this is a operator on infinite dimensional spaces, but it's a very nice operator. So its spectrum actually consists just of eigenvalues. There's nothing other in the spectrum. This is this Fredholm operator for index 0, and we have compact inclusion of W1 into L2. This then implies that this spectrum only consists of eigenvalues. So we don't need to worry about other elements in the spectrum. And now we can define mu eta. So it depends on, of course, on S, but this is just W of V, where V is eigenvector of AS to eigenvalue. So this is the binding number of an eigenvalue. And by the lemma, it's well defined. So let us look at a special case, namely let us look at the spectrum for S equals 0. So the case S equals 0. So there we have our operator is just minus j dt. No ice. And then here is quite easy to compute eigenvalues and eigenvectors. So the eigenvalues, this case are just 2 pi L, where L is in Z, and the eigenvectors this V0 e to the 2 pi I L t, V0 is C. But V0 can be any complex number. So the eigenspace is actually two-dimensional. And the binding number is very easy to compute. It's just L. So then we have the binding number of 2 pi L at 0. This is L. Now we consider any S, but then we have homotopy from 0 to S. So we have S now some smooth map from 0, 1 to the symmetric 2 times 2 matrices. And we consider homotopy Rs, where R is in 0, 1. And so let's. So here is R, and I draw the eigenvalues. for each r. So r equals 0, then we just compute it. So there is one at minus 4 pi, there is one at minus 2 pi, there are actually two. There are two. It's multiplicity 2. And there is at 0, and then is 2 pi, 4 pi, and so on. And then if we switch on S, then they will usually become different. So they come out 2 of this. And here also come out 2 of this. Here come out 2 of this. Here also 2. And then these 2 might also cross some point. So it might be that they cross like this. But something cannot happen. So this here cannot cross this here. Because because of the lemma. Because of the lemma. So they have the so this binding number only depends. They have different binding numbers. So this has binding number 2, minus 2. This has binding number 1, minus 1. So by the lemma, they cannot cross. Because this binding number only depends on the eigenvalue, not on the eigenvector. So here is L equals as a binding number equals minus 2. Here is minus 1, and so on. So they cannot cross. So what can so they can cross. So they can maybe move, but then they cross and move. Maybe not so fast. Happens something like this. But what does not happen, also not by lemma, not possible.
Excuse me.
Yeah.
So this graph for why each eigenvalue have 2 expressions. Do you assume that or?
Yeah, because it's no, because it's we have multiplicity 2. Multiplicity is 2 at 0. And then if you perturb, so then you, as it might be that they stay longer together with multiplicity 2, but generically they will then you will have 2, but then they might cross again. Clear? Yep. So by lemma, this is not possible. Let's have minus 4 pi, it's 2 pi, so we have this 2, maybe they cross, but then this is not possible. Let's focus. So this gives us, so as a further corollary of the lemma, we have the monotonicity. So corollary we have monotonicity. So if S is in infinity, 0, 1, 2, then the map, so W, from the spectrum into Z, which maps an eigenvalue to its binding number, is monotonic. It's monotone, i.e., if eta is less than or equal to eta prime, it follows that W eta is less than or equal W eta prime. Now we define following two quantities. So we define alpha of S. This is the maximum of the binding number of a negative eigenvalue, where eta is eigenvalue of AS, which is negative. So this is integer. But then we have, because we have two of the same binding number, so we have a bit more information. So we also define another number, PS. This number, this is 0 if there exists a non-negative eigenvalue such that alpha S equals W eta S. So this happens if one of the two is already, maybe in this case, this stays still. This would be the biggest one, which is still negative. So in this case, it would this alpha S would be -1, but the other one is already crossed. So we have here 0, and it's 1 else. So this parity, this is just in 0 and 1. And then we define the Conley-Sender index. Conley-Sender index. So mu Conley-Sender of, so this path of symplectic matrices, this is 2 alpha S plus parity. And now I think for today this is enough. So that, so you have maybe seen a definition of the Conley-Sender index. Who has seen a definition of the Conley-Sender index? Yeah. If somebody has seen one, who has seen this definition? Probably nobody. But if somebody has seen another one, then this is actually equivalent to this. But this only makes sense in dimension 2. So we cannot generalize this to higher dimension. So with these binding numbers, otherwise we would have maps to R to n, and then we would get, if we divide by the length, we have a map from S1 to S to n minus 1. So there's no degree. So with this degree, this only makes sense in two-dimensional symplectic vector spaces. But on the other hand, this will be quite useful to control finite energy planes. Because this tells you how these finite energy planes wind close to the asymptotic orbit. And so then we can use this definition to study this intersection properties of these finite energy planes. So this we'll do in next lecture. Questions so far?